This is essentially, this session is essentially about putting things together, really, because from now on, the topological spaces that we are interested in are, the ones that are, constructed through the, through the metric space structure. In this case, subsets of Rn. We know that Rn, through the, previous example slides, Rn is a metric space, okay? And actually, you will see that actually there are not just metric-induced topologies are interesting. There are actually spaces that cannot be metrizable. You cannot add the concept of distance to them. We'll see that in a minute. Topology, as you can see, is very simple. So giving any metric space, the claim is that the collection of subsets that I label TD, which is made of all the subsets of M that are open in respect to D. The claim is that this is a topology on M, okay? And I claim this is trivial because this is a consequence of this. I will go back again. Sorry, properties of open sets. So this is essentially this. So if you can prove this, this is already the thing. This is already telling you that these three points are already telling you that this is true. Okay, so TD is called a metric topology on M. Okay, so it's or the topology induced by the metric D. So we often write this just to differentiate. We put D in this case to make it obvious that there is an underlying metric being considered, as opposed to just this calligraph tau or T, whatever this thing is called. And most importantly, very interestingly, is when M equals Rn and D is the Euclidean metric, then the induced topology is called the standard topology. So it's called standard topology, but it's like, I'm not sure if I like the word standard, but it's more of an accidental term than really standard in the colloquial sense. Okay, so when you hear standard topology, just it means that it's the topology induced by the Euclidean distance. Okay. Most topological spaces of interest in applied topics, like physics and these things, will be subspaces of Rn. Okay, so for us, whenever we say this topology to be a standard topology, so when I say standard topology, just assume that M will be like some sort of a subset of Rn. Okay, it could be Rn itself, but mostly it will be a proper subset of Rn, as we'll see some examples in a minute. Okay. Now here's the thing. I'm already saying this way, I'm getting ahead of myself of the session. Can you see why the metric induced topology is a Hausdorff space? Can anyone see that indeed it's a Hausdorff space? We will see the proof of this in the next few slides. No? Okay, that's fine. Don't worry. You will see this. The key takeaway is that this is very important. Okay, so when we talk about standard topology, we mean the topology induced by the Euclidean metric. Okay, obviously you will ask, this is actually a very interesting question. You might ask, well, but we can equip Rn with other metrics, right? Other distances. There are other distances that you can equip them with. And then you will ask, does it make any difference? Well, I will leave that as a challenge, but there's something else that will determine. Once we get to the notion of equivalent metrics, we will get there. I mean, you will be able to answer, or at least have some sort of a sense whether it makes any difference. Okay, so there you go. This is what I call VIP spaces. I hope I didn't make any typo again, but yeah. So the first one is obviously the circle. Okay, so this is the circle. Set of points in R2 that satisfies this. The claim is that this the subspace topology induced by the standard topology in Rn makes S1 into a topological space. So this is where you will have to start connecting the dots. You remember how to construct the subspace topology, from the first session. So essentially, you will apply that to this. But in this case, you already know, what the standard topology is, right? Is the topology induced by the metric space structure of R2, right? Or more generally, you have this Sn, which is all the set of all points in Rn plus 1 that satisfies this. Okay, so in topological lingo, this is called N sphere. Okay, so. So the claim is this is this thing. In fact, these guys are the prototypes of topological manifolds, which is the topic of interest to us in the manifold section. Okay, at the moment you don't know that they are topological manifolds because we don't know yet what a manifold is. This is there are extra conditions that they have to satisfy, but for the time being, this is you can see. I hope. And if you are struggling to see this, that's fine. But I recommend you to wrap your head around this in the next before the next session to see that this is a topological space. Okay, so you need to be able to see that this is a topological space. If not, you will struggle on the manifold section. Okay, and another interesting space is this one. This space here, because this obviously this is a subset of R, and obviously with the induced, equipped with the subspace topology structure, it's a topological space. Okay, so this is actually a very interesting space because it will help us to define the so-called path-connected topological spaces. This is to not mistake with there's another concept called connected topological spaces. Okay, they're actually independent notion, but one is if, for example, you will see that one leads to the other. For example, connected topological spaces are connected. Sorry, path-connected topological spaces are connected, but connected topological spaces don't need to be path-connected. Okay, so, and here's a hint. Can you think of a reason why the VIP spaces are Hausdorff? They are also Hausdorff, right? Remember what one of the nicest properties. Remember one of the nicest properties that we mentioned in lecture 1 is that any subspace of a Hausdorff is also a Hausdorff. Okay, so I already hinted that Rn is a Hausdorff. Then any subspace will also be Hausdorff. Yes, so Barry's saying seems intuitively true. So Amir, the question is why not other spaces? So this is the ones that I decided to highlight, but in the manifold section we will come construct more examples. Okay, and actually I have some challenges for you with the other topological spaces. Okay. Now, here's the first one is the homeomorphism challenge. Okay, so you know what the homeomorphism, we covered that last week. It's just we covered it in the abstract sense. Now that you know what the standard topology is, like a concrete interest in topology. So, I will challenge you with this, For example, consider this space, this open interval, and this one constructed from obviously the inheriting the subspace topology from the standard topology on R. The question is if this map defined like this is a homeomorphism. Okay, I will not answer. This is a challenge, so you can try to connect the concept, the abstract concept of homeomorphism that we defined in the point set topology section with this. Okay, so you know what a homeomorphism is. You should know if you checked you attended, you watched the previous session. So. And another question is a challenge is this. So given this space and R, can you construct a homeomorphism from X to another subset? Not obviously this is a subset of R, but I don't want it. I want another subset. In other words, is X homeomorphic to any other subsets of R? Is there any other subset of R that's homeomorphic to this? Well, so the challenge is that. And here's another challenge. This might not be like that thing. It will take a bit of head scratching, I hope, for most of you. But is it true that the circle S1 is homeomorphic to this space? In other words, is there a homeomorphism between S1 to X? Okay, I'll leave this as a homework challenge. Okay, and this is where I encourage you. You started to see already, the stuff, the challenging become maybe a little bit harder, even though concrete, helpful. Especially those of you who have like a calculus and analysis background. For those of you who don't have the analysis and the calculus background, things from now on, things will start to become a little bit harder, but I don't discourage you. I would encourage you to join the Discord and connect with the others. Maybe they can help you. Okay. So this is a very simple homeomorphism challenge. There will be more challenges as we go along, as we go through, construct other interesting spaces, especially in the manifold section. Okay, so I was talking about equivalent metrics. I was saying that the same set, can have different metrics, and so from the point of view of open sets, they might generate completely different open sets. Okay, so in that case, when we have two metrics on the same sets with the corresponding topologies, induced topologies, the two metrics are said to be equivalent if they generate the same open sets. Okay, so if the topology is induced by D1 and D2 are the same, then we say that the two metrics are equivalent. So it doesn't matter, whether you pick one or you pick the other. From a topological point of view, they generate the same open sets. Okay, they give you the same topological structure. Okay, so the question is, this is very, here's a toy example. So we have, let's M be any set defined like this. Let's define D1 like this, and define D2 like this. Why not? So in here we have D1 of X1, D1 of XY equals 1 if X is different than Y, 0 if X equals Y. And then we have D2 of XY equals 2021, which is, well, the year that we are, and why not? If X is different than Y, 0 otherwise. Okay, so the question is, I claim that these two are metrics. Okay, they define metrics. The question is if they are equivalent. Okay, I'll leave this as a challenge. Now, another question I leave to you is, supposing that M is Rn and D is the Euclidean metric with the corresponding standard topology TD, can you find other metrics defined in Rn that generate the same open sets? Okay. So think of other, distance, other distances that can be non-Euclidean type of, not non-Euclidean, non-Euclidean distance. I mean, a distance different than the Euclidean distance that can be constructed on Rn that yield the same open sets. I claim there are. So the challenge is, can you find at least one? Okay, so can you see the slides again? Sorry for that.
Yes.
Okay, cool. Okay, so Amir, I was saying, Amir, you are on the thing, on the right track about, I saw something pop up before. I cannot see the messages again, maybe because I left and joined. But yeah, you are on the right track. Okay. Can see the same thing. Okay. what is as the standard topology. Okay,
Yeah,
there's now a
there is
problem
some
with the audio. I may
serious
say.
lag with
So,
the
Ham, can you
audio.
hear me?
Yeah, I can hear you sometimes, but there is some lag in that, so it's getting better. And I mean now it's
Okay,
better, but
sorry for that.
yeah.
Okay, cool. So I better rush through the slides before before the lag gets worse. So yeah, so there you go. This is what you already suspected, that any metric space, for any given metric space, the induced topological space is a Hausdorff space. So I have a lazy proof here. I hope I didn't make any errors. If I did, it's great actually that you can correct me. But I will leave this just in case for you guys to, in case this is helpful for you to see this. But I encourage you to try to prove it yourself first before you even look at this or look at the other proofs on the reference material or something. Okay. And any correction, any loophole on the thing, is also welcome. It means you are switched on. Okay. So another comment I want to say is, so I put a picture here. I hope you can see it. It's very interesting, right? That we can, from a metric space, we can construct topological spaces. What about the other way around? If we are given, so in this case, we have the metric spaces here, we can go down to the topological level, right? We can build the corresponding topological space. The question is, can we do the other way around? Given a topological space, can we get the a structure of a metric space? Okay, and the answer is not always, but when that happens, it gives us the concept of mattressable topological spaces. Okay, so a topological space is mattressable. So we say that x and tau or t is mattressable if there exists a metric on x such that the open sets of the topology coincides with the open set of the topology induced by the metric D. Okay, and now I leave some challenge for you to see whether this topology is mattressable. Can you indeed find a distance, a metric on X that yields the same open sets as this, and the same with this? And also these other spaces that we already encountered in lecture 1, like the Sierpinski topological spaces, whether this is also mattressable. Okay, and I leave you also as a challenge. This is all to make you think about this stuff. Okay, that's why I'm not giving an answer. Obviously, if you pick the reference materials, you might see the answer, but I encourage you to try to find the answer for yourself. Okay. And another tricky question, the notion of space-time to have a notion of distance, for instance. Okay, but in mathematics it doesn't, because this Zarinsky topology, this is a very important topology in algebraic geometry, and yet it's not metrizable. So you cannot talk about the notion of distance. Okay, so just as a side note, you don't need to know all about this, but just to let you know that topological spaces, not just metrizable topological spaces that are interesting from a mathematical point of view. Non-metrizable ones like Zarinsky are very important too. Okay. Okay, so for the reference study materials, I still recommend for you to review some of the concepts, like obviously this Moncres. But now that we are talking about metric spaces, I recommend this is free. For those of you who have joined us before, I think I have a URL for you can download these two. But this one is not free. At least I couldn't find anywhere free. We couldn't get it. But it doesn't matter anyway, because if you find also another good reference on metric spaces and topological spaces, that should do also. Okay, so I recommend the thing as a refresher in case you need help to go through stuff. I'm still online, right? Okay, thank you, Soham. Okay, so before we take a poll, please stay because you will inform and when we should have the next session. So the study materials, I mean the stuff and the link to download the books that I was just saying that we have it for free. You can find it in the repository in this repository in GitHub. The replay of this session, I really recommend that you watch a replay because of the interruptions and these things. I will try to edit it, obviously. And then join the Discord, especially those of you who are struggling with some of the stuff because of, you didn't do analysis or calculus, for instance, join the Discord and connect with the others. And obviously follow us on Twitter and social media stuff to subscribe to our newsletter and these things so you can get latest updates, okay? So now I'll just enable the poll. Please take it so you can dictate. It should be visible. There should be a poll visible under. Let me put my video again. Hopefully it doesn't break. So there should be a poll on the menu bar asking when you want the next session to be. Hopefully by then I should have a better network, I hope. Okay. It's very close, huh? Okay, so far 66% said August the 13th. So you want like the 2 weekly stuff. Is there anyone else who want to vote, who hasn't voted yet? Okay. Well, in that case, then I think Friday, August the 13th is the next session then, to give you enough time to wrap your head around the standard topology stuff, okay? The stuff that you do, because we are now getting into the realms of the stuff that will lead us to manifolds, okay? Okay, someone is saying just need to make it to the end of my current school semester, then I might be open to weekly. Okay, yeah. For me, it's really the most important thing is really that you have enough time to observe the stuff, because if you struggle with the previous session, the concept, the notions that are, it will make it very hard for you to catch up to the next session, because things are built on top of each other. Okay, so I would rather that you have enough time to refresh yourselves than rushing just in order to get the crash course out of the way, because at the end of the day we want this crash course, so we have a clear goal that we want to get out of this crash course, which is essentially to know what differentiable manifolds, smooth manifolds are, and these things. Any other stuff are obviously bonus for other for other purposes. But it's very important that you have the chance to wrap your head around stuff. That's one of the reasons I've split all these things in small chunks to make it easy for you. In reality, we could have covered a lot of stuff just in 2 or 3 sessions. But I'm just focused on the things steering you towards the stuff that we need. Because these are like massive topics. Metric spaces is massive topic. Point set topology is massive, and these things. But hopefully the way I organize it, make it easier for you to learn what you need for our purposes anyway. Okay, so we will catch up on Friday, August 13th. So Ham, I don't know if you want to make any comment. Is there anything that I missed or any feedback?
No, I think this is fine. Yep, yeah. And I look forward to Friday, August 13th. Hopefully, I'll be able to make that.
Yeah. Anyone else? Any other comment elsewhere, Soham, that I haven't seen,
No,
or question?
no, I don't think there are any further questions that you might have missed. So yeah, that seems to
Yeah.
be all.
George is offering to a study session. Yeah, I definitely recommend you join George, please. It will make it, especially the stuff that you are confused about. It makes it far more easier. If you have someone, a companion that you can study with. If George is not in a convenient time zone with you, find another community member. That's why I would like you to join the Discord, right? So you can connect with others and um, do like joint sessions together. Okay. So a final thing before we go, I know we are running off the time. From those who are still, how is it in terms of abstraction? How do you find it? The thing I think now is becoming, especially for those of you who done analysis and calculus, things are starting to be more, even though you were doing things like in the calculus and the thing, it's much easier now for you to connect the abstract concept, the topological concept, to stuff that you were already familiar with.
Yep. Yeah, I agree.
Do you agree?
Yeah.
Which is why the reason I didn't want to spend so much time on point set, abstract set, theoretic oriented, heavy stuff on topology, in order to get us to metric topology, because then we can still define the other topological concept that we could have done in the point set section, but then it makes it easier for you to see the examples, like some of the stuff that we will define in the next session. Okay, so. If you don't have anything else, I know we are running away, and apologies again for the for the networking issues. It's just I'm in a temporary place here. At the moment, the network is not good, but yeah, hopefully the next session will run smoother than today. Okay, so in that case, if no one else has any questions, I see you guys on Friday the 13th in 2 weeks' time. We are really getting well done. We are really getting into the thing, into the actual interesting stuff that will lead us to manifolds. Very interesting stuff. For those of you, as I already mentioned in the thing in the newsletter or something, this is not just actually just pure topology. You will have some elements of differential geometry into this, especially in the manifold section. So this the stuff that we are going through, all this painful stuff, is like it's all necessary stuff for you to be able to see the cool stuff that we will come to, the more advanced stuff. Okay, so yeah, with that I will stop blah blah stuff, and yeah, we see you next week, sorry, in 2 weeks time. And thank you again for showing up, and thank you again to our friend Soham for helping.
No worries.
Okay,
Thank
bye.
you.
I see you guys.
Bye.
Yeah.
See you.